In the quantum world, reality behaves in ways that seem almost magical. A particle can exist in multiple places at once, and Schrödinger's famous thought experiment describes a cat that's both alive and dead until observed. But here's the big question. How does our familiar, predictable, classical world arise from such a strange, probabilistic realm? Let's break it down. At the heart of quantum mechanics lies the wave function, a mathematical description of all the possible states a system can exist in. But there's a twist. We don't see all these possibilities playing out at once in the world around us. Instead, we observe only one specific outcome. This is where the Born rule comes in. It tells us that the probability of observing a certain outcome depends on the square of the wave function's amplitude for that state. In essence, it's a recipe for predicting probabilities. But the question remains, how do these probabilities turn into the single, definite outcomes we see in the classical world? Recent numerical simulations have shed new light on how the classical world might emerge naturally from the quantum one. They highlight three key mechanisms. When a quantum system interacts with its environment, it loses its quantum weirdness, or coherence. The system starts behaving more predictably, like a classical object. Certain quantum states become more likely than others due to their interactions with the environment, essentially choosing the outcome we observe. Over time, quantum probabilities align with the expectations of classical physics, reinforcing the Born rule's predictions. In short, the environment plays a massive role in translating quantum probabilities into the deterministic behavior we see in the everyday world. Let's go back to Schrödinger's cat, sitting in its sealed box, both alive and dead in the quantum world. What these simulations suggest is that the environment around the cat, even the air molecules in the box, forces one outcome to dominate over the other. In other words, there's no magical collapse of the wave function. Instead, one outcome becomes overwhelmingly probable due to interactions with the surroundings. The cat is never truly both alive and dead. The classical world simply emerges naturally from the quantum one. Understanding how the classical world emerges from quantum mechanics isn't just an academic exercise. It has real-world implications. It offers new clarity about the nature of reality and the role of observation in quantum mechanics. It could revolutionize quantum computing, where controlling decoherence is one of the biggest challenges. It bridges the gap between quantum uncertainty and classical determinism, helping us understand how the microscopic and macroscopic worlds connect. These findings are just the beginning. Future simulations of larger, more complex systems could reveal even more about how the classical world emerges from the quantum fabric of reality. And as quantum computers continue to develop, they could provide experimental proof of these insights. So, the next time you marvel at the predictability of the classical world, remember that beneath it lies the chaos and beauty of quantum mechanics, where probabilities dance and the universe speaks in waves.